It's variation of parameters time. I've been putting this off all day, as you can see in the top left. It is 10:25 p.m. We'll see how long this one takes, but I have a huge backlog of things to go through for these finals, like a heinous amount of recording over the next 3 weeks. Wish me luck. But now all we're doing is just some variation in parameters. We know that if we have our fundamental solutions for the homogeneous equation here, so our characteristic solutions, we can say that y particular of t is equal to negative y1 of t, our first fundamental solution, times the integral of y2 of t times f of t over the Wronskian of our two fundamental solutions, dt, plus y2 of t times the integral of y1 of t times f of t over the Wronskian dt. And f of t is anything that's on the right as long as our coefficient on y double prime is 1. So let's just get going. This is the only time I'm going to write out this formula, so commit it to memory if you don't already have it. It comes pretty quickly. There is a nice pattern to it. It's not completely random, but we have a couple of things to find. Let's solve our characteristic equation. R squared plus 4 equals 0. That's r is equal to plus or minus 2i. So our solutions to our yc is c1 cosine 2t plus c2 sine 2t. So that means y1 of t is equal to cosine 2t, and y2 of t is equal to sine 2t. That is good for us to know. Then we also need the Wronskian of these solutions, which is the determinant of the matrix formed by cosine 2t sine 2t, and then their first derivatives. That gives us negative 2 sine 2t and 2 cosine 2t. You can see just visually that this determinant will give us 2 cosine squared t plus 2 sine squared t, which is just equal to 2. So our Wronskian is 2, and then our f of t, because our coefficient on y double prime is 1, f of t is just 1 over cosine 2t. So setting everything up, we have minus cosine 2t, that's our minus y1. Our Wronskian is 2. F of t is cosine 1 over cosine 2t, so I'll put that down here. And y of 2 is sine 2t. Then we are going to add y2 sine 2t, and here we'll get 2 cosine 2t, just like we did before, but instead of sine 2t, we'll have cosine 2t dt on top. This integral simplifies down pretty nicely to 1 over 2, so we will get sine of 2t times 1 over 2t, and that's already pointing us at option D, but let's make sure that this integral evaluates correctly. Let's do a u substitution where u is equal to cosine 2t, and I'll factor this 2 out. Du is equal to negative 2 sine 2t, so we can rewrite this integral as dt, as the integral of negative cosine 2t over 2 multiplied outside, and then in here we have 1 over u times 1 over negative 2, and I'll bring that negative 2 out, and that'll give us plus 4 dt. This gives us cosine 2t over 4 times the natural log of the absolute magnitude of u, the absolute value of u, which is cosine 2t. So we take this, add it with what we had up there, and it does lead us, in fact, to option D. Okay, we have a homogeneous differential equation here with two fundamental solutions. I'll just write them out here. y1 of t is t squared, y2 of t is t cubed. We're using variation of parameters to find a solution to this non-homogeneous differential equation. We know that the right-hand side is only equal to f of t if we divide out any coefficients that we have on y double prime. So dividing that t squared over, we see that f of t is equal to t. Finding the Wronskian of these two solutions will just be t squared, t cubed, 2t squared, 3t squared. And this is actually, sorry, 2t. This determinant will give us 3t to the fourth minus 2t to the fourth, which is just t to the fourth. Yes, just making sure I did my math right. And so our Wronskian is t to the fourth. So we can directly set up negative t squared multiplied by the integral of t cubed times t over t to the fourth dt plus t cubed times the integral of t squared times t over t to the fourth dt. This will become 1 over t, and so it will evaluate to ln t, although they're not using the absolute value for whatever reason. And then we have our t to the fourth. Oh, that's why. There's our reason, for t greater than 0. It's always something. Okay, and then this will simplify down to 1 dt, so we'll get t cubed out here. And so we can set up our y of t as our c1 t squared plus c2 t cubed, our solutions to our characteristic equation with the constants on them, because we don't have the initial conditions that would allow us to solve for those, and then minus. I did something wrong somewhere, didn't I? No, I didn't. Haha. This one tricked me before, and I bet it tricked you too. It's a weird little trick they're pulling here. Okay, I'm glad I don't have it wrong though. This minus 1 times t cubed can be, I don't know why this t cubed is t cubed. There we go. This minus 1 t cubed can be absorbed into this c. We can factor that out and say that c2 minus 1 times t cubed is just some other constant. So in fact, we can get rid of this entirely, and this is still a valid solution. So that leads us to option A. Phew. 14. y1 is root t and y2 is 1 over t. And they are the solutions to this linear homogeneous differential equation. And we're told to use variation parameters to find a solution to this guy right here. We are given that y1 of t is root t and y2 of t is 1 over t. We can find the Wronskian. That will be root t. I'll actually put it into t to the 1/2 form, and then we'll have 1/2 t to the negative 1/2 here, 1 over t negative 1 over t squared. You can already tell this problem is going to get pretty disgusting pretty quickly, which it most definitely does. Multiplying this out, I'll write this as negative t to the negative 2, and this as t to the negative 1. And then really this is 4. I need to do all this to make sure I'm not messing anything up along the way. So this determinant will give us negative t to the negative 3 over 2, and then we're subtracting 1/2 t to the negative 3 over 2, so we get our Wronskian as negative 3 over 2 t to the negative 3 over 2. I remember that number from doing this in the past, so I think we're on, pretty sure we are on the right track. And then finally, we need our f of t, which is only the right-hand side over here when we divide out this 2t squared. So we will get 2 plus 2t to the negative 1 power. Is that right? I'm in a questioning myself mood tonight. 2, and then, yeah, 2 over t. Okay, good. And this is our f of t. So now setting up everything, we have negative y1, so negative root t, times the integral of y2 of t, so t to the negative 1, times f of t, 2 plus 2t to the negative 1, all divided by our Wronskian, negative 3 over 2t to the negative 3 over 2. We can take this negative 3 over 2 from our denominator outside as 2/3 and move on to our second integral, plus 1 over t times the integral of t to the 1/2 times f of t, 2 plus 2t to the negative 1, all divided by t to the negative 3 over 2, and again I'll bring the 2 over 3 out like that. Oh God, this is not going to be fun, but we might be past the worst of it already. Expanding our numerators of both of these integrals, we will have 2t to the minus 1 and plus 2t to the minus 2 there, and then over here 2t to the 1/2 plus 2t to the negative 1/2. Great. What are we going to do now? Well, because we have a t to the negative 3/2 on the bottom, we can bring that up to the top and multiply everything by t to the 3/2. So we're adding 3 over 2 to all of these powers. This will give us 1 over 2 here and negative 1 over 2 here. And then adding 3 over 2 to all of these powers will give us t squared and t to the first, like so. Just going to shuffle some things around. And in fact, I'm going to get rid of that entire integral. This will be the one that we're working off for now. Okay, we can go ahead and compute both of these. We will have 2 over 3 root t times the quantity terrible. I'm absolutely terrible at this. I shouldn't be recording right now, but here we are. 2 times 3 over 2 times 2 over 3 times t to the 3/2 plus 2 times 2 t to the 1/2. And then we have plus 2/3 times 1 over t, 2 over 3 t cubed plus t squared. We are getting there. This will be 4 over 3 and 4 like that. Let's factor in our 2/3 power. That will give us 8 over 9 here and 8 over 3. 8 over 9 and 8 over 3. Something doesn't seem right about that, but I'm going to continue. Then over here we get 4 over 9. 4 over 9. 4 over 9 and 2 over 3. I'm just distracting myself with the thought that I might be wrong. Okay, we have 8 over 9 t squared plus 8 over 3 t plus 4 over 9 t squared plus 2 over 3 t. 2 over 3 t plus 8 over 3 t. Well, let's put that That will be 10 over 3, which is in, and I'm sure it's completely infuriating for you if you were following along and either you caught me doing it or now you're not sure where it happened. I'm not sure where it happened either, but I know that we lost a negative sign here. And I'm guessing it was from, actually, that's where it was from. We had this negative 3 over 2 in our denominator, and we factored it out as a 2 over 3 instead of a negative 2 over 3, because the sign that used to be there was a positive sign. So that will change this into minus 4 over 9 and minus 2 over 3. That gives us 4 over 9 t squared plus 6 over 3t, so plus 2t. And that gives us answer A when we add in our fundamental solution portion. 9. The general solution to this homogeneous differential equation is given by this thing. We're applying variation of parameters to find a particular solution. So collecting the four terms that we need, we have y1 of t, that's x squared. y2 of t is x squared ln x. The Wronskian is going to be x squared 2x x squared ln x, 2x ln x plus x, and we're computing this determinant. That will be 2x cubed ln x plus x cubed minus 2x cubed ln x. So we just get x cubed as our Wronskian. W equals x cubed. And then finally, we need our f of t, which is our right-hand side when we divide out any thing on y double prime. So that gives us 5 ln x. F of t is 5 ln x. Now setting up negative y1, negative x squared, times the integral of y2, so x squared ln x times 5 ln x. So there we go, that's multiplying by our f of t, and we are dividing everything. We're dividing everything by our Wronskian, which is x cubed, and I'll just go ahead and simplify. Simplify now. Dx plus y2, sorry, x squared ln x times the integral of y1 x squared over x cubed multiplied by 5 ln x. That gives us 5 ln x over x dx. Now doing a u substitution, we can say that u is ln x, du is 1 over x dx. So this integral, this left-hand integral, I'll take it over here, is negative x squared times the integral of 5u squared du. That will give us negative, I need more space. Okay, I guess that integral sign's going with it. That's negative x squared times 5 over 3 u cubed, so ln x cubed. So there's half of our solution right there. And I do this every time. Every time I do this question, I go through the whole motions and solve the entire problem. This is why you should really read the question. Even though I've done this one, I don't know, 5 or 6 times at this point, I still every single time go all the way through. And that's because I fail to read that what they're looking for is u1 prime and u2 prime, where u1 and u2 are the things multiplied by our fundamental solutions. So that will be this thing, the derivative of this thing, and the derivative of this thing. Well, what's the derivative of the derivative of an integral? That just gives us the integrand. So we will have negative 5 ln x squared over x as u1, and that is right here, and then u2x follows 5 ln x over x. Gotta read the question. Okay, 7, we have a differential equation with some fundamental solutions, and we're using, again, variation of parameters. Dividing out our x squared here, we see that f of t is 1 over x. This is actually x. They're switching it up on us. y1 of t is x. y2 of t is x ln x. And then our Wronskian is the determinant of x1, x ln x, and then ln x plus 1. That will give us x ln x plus x minus x ln x, just giving us x. Wronskian is x. So we have to compute negative y1, so negative x times the integral of y2, which is x ln x, multiplied by f of x. That's 1 over x. That'll just divide out that x all over a Wronskian, which is x dx, plus y2, which is x ln x, times the integral of y1, which is x, multiplied by f of x, which is 1 over x, all divided by our Wronskian dx. This will just evaluate to ln x, so we can square that guy and call it a day. And over here, we can say that u is equal to ln x, du is equal to 1 over x dx. So this integral is negative x times the integral of u du. That is just u squared over 2, where u is ln x. So putting these two together, and not losing that negative sign. So overall, we get x ln x squared over 2, which is c, and we're done.